Okay, good morning all of you. My screen is visible. Anybody? Hello.
Yes, sir.
Screen is visible now.
Yes, sir.
Okay. We'll see today dynamic characteristics and protection of SCRs. We'll see whether it will complete protection total or some of the protection schemes will see the next class. These are the two topics we are going to explain. One is a dynamic characteristics, another one is a protection of SCR. And the rest points that is series parallel triggering circuits, commutation circuit in the further classes. And we can notice that in the case of static characteristics, we observed three modes of operation: forward blocking, forward conduction, reverse blocking, like that. So in this case, when the thyristor is forward bias, only at that instant only we can able to turn on the device by giving the gate signal and all. Here, to turn on thyristor, applying a positive voltage between gate and cathode terminals. So that means from the yesterday's class we observed that finally gate triggering is a preferable method. So in that concept we can see that to turn on the SCR we need to apply voltage across gate and cathode terminals, but it takes some time to go from forward blocking mode to forward conduction mode. So why? Because the device is already in the off state, means it is a forward blocking mode. That means outer junctions are forward bias, only inner junction is a reverse bias. You need to break the inner junction to conduct the SCR. This transition time, means from off state to on state, is called a turn on time of a SCR. Directly it won't be happen immediately. Of course it may be very less time only, but in between how the currents will rise and how the voltage is going to fall down, all these things will notice. This transition period from off state to on state, that we call it as a turn on time of a SCR. That for our convenience we subdivided into small intervals, that is a delay time, rise time and spread time. So some books they mention only two things. One is a delay time and rise time. The spread time, it is just optional, it is very small time only. Anyhow, I will explain that part also. So these are the three intervals. Some of these three intervals is nothing but a turn on time. So T on is nothing but a delay time plus rise time plus spread time. Now this is the diagram. If you notice, turn on time of SCR, some of the graphs I plotted, we can notice the things. First one, this curve is nothing but a voltage, anode voltage, and this one we call it as a gate current. And second graph we can see this, there is a anode current, and final one is a power loss or switching losses. This we call it as a, just a minute, I will shade this portion. This is nothing but a losses. Whatever the yellow shade is there, that one we call it as a loss. Now we can see this during turn on process you will get some loss. So that loss we call it as a on loss or a switching loss during device is going to be on. For that, as I said, initially device is off state. When the device is off state, What is the meaning? Voltage, as you know that output voltage is 0 if device is off state, and voltage across the device is same as the source voltage. Similarly, if we come to the current case, if the device is off state, means switch is open, the current is 0, and that is a load current, let it be, or anode current. Another one, suppose if we consider as a gate current, a device is off state, gate current is 0. So when the device is on state, what is the meaning? Anode current will be there. This will be gradually rising, and to turn on we required as a gate current initially 0, and we have to apply some gate current. So this is the normal basic rules. Now we can see these characteristics. This area, whatever we will mention, that area is nothing but a, what is this area? This side area is off state. So from off state, it is going to be on. In this area is going to turn on the device. So that is the reason initially device is off state. The voltage across the device is same as the source. That's why we started high value or a rated value or whatever you apply to that. That we call it as a voltage across the device because it is in the off state. Now you can see the gate current. So what is the gate current when the device is off state? Gate current is 0 because we don't want to give any gate signal when the device is in the off state. Now what about the anode current? Anode current is a 0 or very small amount of the leakage current. So that is a forward leakage current. This is nothing but a very small magnitude because J1, J3 are forward bias, J2 is reverse bias. Very small leakage current pass through the junction J2. And now what about this side? The device is off state at moment. You can see that the loss also 0 because voltage is 0, and then voltage is there but current is very small, negligible current, and you can see that very small amount of loss will be there. That is the initial status. Now what I want to do is I want to turn on the device from off state to on state, and in between some process is there. Let's assume that the device is completely on. Then what is meaning? Device is completely on in the sense we are giving as a gate signal. That's why current is there, and once it is completely on, what is the voltage across the device? It is 0, or strictly speaking there is a 1 to 2 volts drop will be there across the device when the device is in the conduction mode, and that's why we can see the voltage is reaches to near to the 0. And what about anode current? Once it is completely on, anode current is equal to the same as the load current. And what about the loss? Once the device is completely on, voltage is very small, and even though current is there, but the drop will be very small because of the product of voltage and current. So that is completely on process, and this side is completely off process. And now means off state to on state. In between what will happen? We'll see that. That is only the dynamic characteristics of a SCR from off state to on state. Now we can see the how many intervals I mentioned? 3 intervals. One is a delay time, rise time, and spread time. And sum of these 3 I call it as a turn on time. Now what is the delay time? We can see 2 ways we can explain that concept or a delay time interval. One is the gate current respect. We can see that delay time we can observe here from this point Here you can see the gate current. If we consider this portion, I call it as a delay time in the gate. And what about anode voltage and current? You can see this portion, and another one is this portion. I call it as a delay. Now we can simply define that gate current to increase from 90 percentage to 100 percentage. So this portion, this is a 90 percentage. From this to 100% means whatever you want to give the gate current, that interval between gate current changes from 90 percentage of its final value to 100 percentage of its final value. So that interval I call it as a delay time. And otherwise also you can see the delay time interval in which anode current, this one is a anode current, you can see anode current reaches, here I will show this marker. Yeah, so anode current reaches 10 percentage of the final value, means leakage current to 10 percentage of its final value, and the same time anode voltage you can see that fall to 90 percentage. It is dropping. Why the voltage is dropping and current is rising? Because device is off state to on state, the voltage has to reaches to the lower value, because if it is completely conduct, short circuit voltage, and when the current is need to rise because it is going to conduct the device or close the switch. So that is the relation you can see here. Anode current rises from forward leakage current to 10 percentage of its final value, and at the same time the voltage will be fall from 100% to 90 percentage of its final value. So either of one is also sufficient. One thing we can define, gate current changes from 90 percentage to 100 percentage, or else the interval anode current changes from reaches to 10 percentage of its final value to anode voltage drops down 100 to 90 percentage of its final value. So that is also that interval we call it as a, what we call it as delay time. And now we can see the rise time. What is the rise time? You can see this gap. This one I call it as a rise time. One simple statement we can mention for the rise time, and the interval, or you can say that the anode current changes from 10 percentage to 90 percentage of its final value. We call it as a rise time. You can see this is gradually anode current changing. Initially only leakage current is there, and delay time it is reaches to 10 percentage, and the rise time interval it is changes 10 to 90 percentage of its final value. That we call it as a rise time. So we can see that current rises from 10 percentage to 90 percentage of its final value. At the same time, if you want to see the voltage also, what will happen? The voltage here 90 percentage to 10 percentage. That shows current is rising gradually, voltage is decreasing gradually. The interval anode current changes from 10 percentage to 90 percentage its final value. At the same time, anode voltage changes from 90 percentage to, what will happen, to 10 percentage of its final value. That I call it as a rise time. The phenomena of decreasing anode voltage and the increasing anode current is entirely depends upon the type of load. So how much time it will take and the nature of that increasing and decreasing this phenomena based on the type of the load, because it is carrying the current from the source to the load by this device. That's why based on the type of the load also the variation and time taken to change that will be decided. Another one is a spread time. So this one we can see here, by seeing this also we can state that what we can get it. Yeah. So now we can see here there is a voltage is near to the 10%. It is reaches already 10%. But here also we can see that current it is almost reaches to the rated value. So that means 90% to its rated value. The time taken to increase the anode current from 90% to 100% or a final value, call it as a spread time. That's what I mentioned there. And at the same time we can see that voltage also already under rise time case voltage is fall down to 10%, but finally it has to reaches to near to 0 or a drop across the device 1 to 2 volts. That's why we mention here decreases from 10% of its initial value to smallest possible value, that is only the drop across the device, that will give only 1 to 2 volts or 1 to 1.5 volts. And in this interval of time conduction spreads all over the area of a cathode, and SCR will get fully turn on. Spread time of SCR depends upon the cross section area of a cathode. So, and now we need to find what is the time taken to turn on the device. So what is time taken to turn on the device? We need to add all the three. So this is a sum of delay time, rise time and spread time. This typically there is a 1 to 4 microseconds of time. You remember this? The turn on time of a device, it is very less time only. So we are able to turn on the device with very small time duration. So whatever process is going to be happen within a 1 to 4 microseconds of time. Now the width of the firing pulse, because all these things will be based on firing pulses. If we give width is very less, within the time that may not be reaches the latching current and device will never fire. And that way we can see that the width and the magnitudes, all these things must be some certain values. The width of the firing pulse should more than 10 microseconds or preferably 20 to 100 microseconds must give firing pulses. So why we specified that? Because within that time duration the device is going to fire. For that we need to allow the gate current or a pulse that much interval. That's what we observed in the previous class, two problems. No, one problem, what is the time is required to device reaches to latching current, and if the time also given whether it is fire or not, like that. So based on this logic, that is the width. Another one is the amplitude of the pulse, that should be 3 to 5 times the minimum gate current required to trigger the SCR. There is a amplitude of the pulse. You can see the pulse will be like this one. So width is specified preferably 10 to 100 microsecond. Then the amplitude is 3 to 5 times of the minimum gate current is required to trigger the SCR. The IG, I told no, IG minimum and IG maximum are specified. Because when you are giving the current, that protection also is required for the gate protection, or if you give continuous current also, there is a power dissipation in the gate circuit that will leads the efficiency of the device. So that will reduce that efficiency. That is the reason Once if the device is triggered, we don't want to give any firing pulses or current or anything across gate and cathode. That's why generally we are giving pulse to trigger it. Once device is triggered, we can remove the pulse. It won't happen anything, it will continue to conduct. So that's why we need to provide the width will be 20 to 100 microsecond, amplitude 3 to 5 times of a minimum gate current. So then we can see that losses. So what is the loss? We can see one important observation from this plot. There is a loss will be high during this instant. After that, loss will be minimum. What is meaning of it? So whatever shaded area, this peak, that will be loss is high. After that, loss is very minute. So the reason behind is during that instant, whatever I am showing loss is high. During that instant, anode current is present, voltage across the device is also present. This is a anode current and this is a voltage across the device. So whatever I shade now, during that instant, the device is changing from off state to on state only during which, what is the time interval? 1 to 4 microseconds of time. Within a time duration, both voltage is present, a little bit maximum voltage only, current also maximum current is present. So if I multiply these two things, then power will give, power loss will give as a more during that instant. But after that interval, we can notice the curve, current is rated but voltage is near to zero. That's why power loss will be decreases. And before that interval, you can see here current is, voltage is more, but current is only the leakage current or very small current. If you multiply that, loss will be minimum. So that is the reason we can see that power loss will be more during switching action, but after completely switched off or completely switched on, we don't get it any losses. That duration I call it as a switching time or a switching losses. So that's why during switching loss interval, we can able to get this interval of time, and that is the way we can able to find the power loss. So power loss will be available during on process, and once completely on it will be 0 and completely off it will be 0. This may result in high instantaneous power dissipation, creating a local internal hotspots that destroy the device, because if this heat is generated within this, so automatically there is a hotspot, and that heat dissipation has to be dissipate soon based on the surface area. If it is less, that instant at any point that will be developed, then the device is going to be destroyed. That is why we need to take necessary to limit the rate of rise of current. If this rate of rise of current is limited, there is a small then only hotspot we can avoid. Otherwise, if it is unable to spread that temperature or something, then there is a one point of time it will be higher temperature, the device is going to be destroyed. To overcome that, we are using as a di by dt inductor inserted in the anode circuit. So whatever we are using as a device, you can see like this, and here we are inserting as a inductor. So di by dt inductor if we place, then we can limit the di by dt, inductor if you place, you can limit the rate of change of current. Like yesterday I mentioned, no, to limit the dV by dt, we need to place one capacitor parallel with the device. Similarly, to limit the di by dt, we required as a one inductor in series with the device. So that we need to place. Now that is all about on process. Now what is extension next? Now device is completely on. Then we need to turn off the device. First instant is initially device is in off state. We made it to on. That time we calculated. Now if the device is on now, you need to turn off the device. That's what I mentioned here. The thyristor is switched on. The other point of view, the anode current is above latching current. It is continue to on. Gate will lose the control over it. That also I mentioned. Once device is on, there is no control over the device. That because if the tap is open, it will go flow of electrons. So similarly, you can see that water. So that way, here what will happen? We already turn on the device, all the junctions are breaks down, the current is passing from anode to cathode. So gate cannot have to stop that. Now it is, you can remove that gate signal thereafter once the device is reaches to the latching current. Now, so gate circuit cannot turn off the device because no control over that. For turning off the SCR, what is the requirement? Anode current must fall below the holding current or make it to 0. Then only device is going to turn off. Otherwise, it will continue to on. Anode current fall to 0. That means whatever anode current is there, that is fall to 0. We cannot apply forward voltage across the device because if the current is 0, but whatever charge particles are there inside, the reason is you can see that like a device is like this layers. If all the layers are open, you are passing like this. Even though if you cut off in this side, but already existing charge particles are present, I need to remove completely that. So for that, turn off time of SCR can be defined as a interval between anode current fall to 0 and device again to block the voltage. What is meaning of blocking the voltage? We can see here once the device is like this. If device is on, there is a current. Now if you make the device current is 0, it will be open. But once the device is open, again what will happen? It will block the voltage. So voltage across the device same as the source voltage. So that is the, if it is completely open. So that process or that interval, I call it as a turn off time. So from 0 current to blocking voltage mode. Based on removing the carrier charges from the 4 layers, that is a turn off time of SCR can be divided into 2 intervals. So all the 4 layers filled with the charge particles, I have to remove it. Then only I can say the device is completely off. Like a fan, no? Once the fan is rotating, if you switch off the fan, why the fan is not 0 speed the moment when you switch off the fan? Because even though if you cut off the input, there is a some kinetic energy stored in that motor, so that has to be dissipated completely. So once it is dissipated, only it is reaches to the 0 speed. While it is dissipating, initially high speed will be there, gradually it reduce the speed, at some point of time it will reaches to completely 0 speed. So like that. So even though you cut off the input, we need to completely remove the charge particles. So there is a two processes are there: reverse recovery time and gate recovery time. So these are the two intervals to remove the charge particles. Now we can see here this process, we can see that there is a current. This is anode current. What is the turn off time I mentioned earlier? Anode current reaches to the 0 to the voltage across this is going to be black. So black in the sense completely open. The voltage across that will be same as the source voltage. So that interval we call it as a turn off interval. So this I divided two things. One I call it as a reverse recovery time. Another one call it as a gate recovery time. Some of these two times I call it as a turn off time, but TC is a little bit more. This is a circuit turn off time. So we have to give some time when the device is completely under a blacking state. For that, thyristor turn off time is different, circuit turn off time is different. So even though thyristor is turn off completely, before fire the next device, you have to give some delay time for reliable commutation. If you immediately fire the next device like inverters and all, both devices are in the same leg. If first device is not completely turn off, if we fire the next one, there is a short circuit is going to be takes place. That is the reason we need to give some delay, that we call it as a total complete circuit turn off time. Now we can see that reverse recovery time. What is the reverse recovery time? There is an interval between T1 to T3. So that we call it as a reverse recovery time. And or in general word I can say that to remove the excess charge particles from the outer junctions, we call it as a reverse recovery time. And now we can see that it is the interval in which the charge carriers removes from J1 and J3. What is J1 and J3? Is nothing but outer junctions. So inner junction is what? J2, because during that on condition there is a charge particles. I have to remove all the things. For that easily we can remove the outer junctions, but inner junction little bit complicated. There we can use as a gate recovery. That interval I call it as a gate or recombination process takes place to remove that inner junction. At the time T1 you can see that this one anode current fall to 0, and it will continue to increase the reverse direction, because there is like a motor as I said. So that kinetic energy is converted into electrical, it rotates. So that means it is reverse, it's flowing. So now current will be 0 and it will continue to increase in the reverse direction with small slope of di by dt to forward decreasing current. Now it will be under gradually develop in the negative current. This negative current will help to sweep out the carrier charge from junction J1 and J3, because already charge particles are there. You are making indirectly opposite direction, so that will be cancelled out. So what will happen? This negative current will sweep out the inner outer junction charge particles, that is a J1 and J3. Now at the instant of T2 carries the charge density is not enough to maintain in the reverse current. So what will happen? We are sweeping the charge particle, some portion is sweep out, and only remaining portion, the density of the charge particles are less, so it cannot fight that in the opposite direction. That's why very sharply the current is going to be reduces to lower value. So it is here we are taking some time, but where there is onwards very sharply it is decreases, or means the remaining charge particles or density will be very less, because already some of the charge particles are removed. So with that the charge particles or current will be gradually reaches to the towards that. So that's the mention I mentioned here. Density is not enough to maintain the reverse current. Hence after T2 the negative current will starts to decay. So that is going to be decreases. Now the at T2 called reverse recovery current. So this current I call it as a reverse recovery current. This time I call it as a reverse recovery time. Due to rapid decrease of anode current, the reverse spike of the voltage may appear across the SCR. Now we can see that this spike is going to happen while it is going to turn off. Now we can see that during on, this voltage, very small voltage will be present, that is a drop across that, and now there is a spike will be obtained. This spike during that, I mean, because the current density is sharply reduced, no, that's why there is a spike will be obtained in the voltage across the device. That's what we mentioned, rapid decrease of the anode current, reverse spike of voltage appear across the device. That spike here we shown little bit smoother, but normally it will be something like spark. So this way is going to be applied. So that means spike is going to be across that. Now there is a total recovery time T3 to T1, that we call it as a reverse recovery time. The statement is to remove the excess charge particles from the outer junction, we call it as a reverse recovery time. So after that starts to flow applied voltage, reverse voltage, and its gain is proportional to the block of the forward voltage. Now it can able to trying to block that forward voltage. But what about the gate recovery time? That means our TGR. TRR is a gate reverse recovery time. TGR is a gate recovery time. So to remove the excess charge particles from the inner junction, I call it as a gate recovery time. So now we can see that after sweeping out the carrier from the outer junction, that is a J1 and J2 during reverse recovery time, the remaining charge particles at the junction J2, so prevent the SCR in the blocking forward voltage. It still there is a charge particles, that's why it is unable to block. But if you do this the inner junction charge particles also, then it is going to be blocked. So removed by combination, that is a recombination only, because it is inner layer, only recombination process we have to do. The recombination is done, that called as a gate recovery time. Now this is the characteristics complete. To understand, what I did is I split this portion into two parts. This part is a on process and this part is a off process. So you can in exam also you can use this portion what I used previous slide for the off process, and this you can use on process separately, or you want to specify at a time also is fine. And in between, what is this? These statements are exactly carry forward from this, because device is completely on, the current will carry, and then this one is a current and voltage will be 0 only, and current will be remain same, and the power loss will be very less. So this is only during, these two things are during on, this one is during off, but what is in between, that is completely under on state position, not a during, it is a completely on state. Once device is completely on, that way we can do it. So that is all about dynamic characteristics of a SCR. Now we'll see the protection of a thyristor. This is very important. Protection of a device is an important aspect for the reliable and efficient operation. So why the reliable term? Suppose if you are unable to protect properly, whether it is a dA by dt or a dV by dt or a temperature or anything, automatically misfunction is going to be takes place. Sometime misfire in the sense conduction, unwanted conduction also going to takes place. So that is what based on the protection mechanism, the reliability is going to be improved. So this device, that thyristor, is a delicate semiconductor device. So we must use it in the specified ratings to get the desired output. So we need to operate the device under normal operating conditions. So some ratings it will not be allowed for the higher current or higher voltages, because normal operating condition only we need to operate the device. face different types of threats during operation. That is either over voltage or a overcurrent. Both cases will be there. Over voltage problems will be there. Over current problems also will be there. So there is a different types of thyristor protection schemes are available for a satisfactory operation of a device. So these protection schemes are going to explain now. So because what are the protection schemes are available in thyristor, and one by one we'll see that. What is that? One is a over voltage protection, over current protection, dv by dt protection, di by dt protection, and thermal or a temperature. So all briefly we aware that di by dt is known, dv by dt is known. That is thermal protection is nothing but a temperature. So that is using heat sink we can protect. So like that we'll see one by one. Di by dt protection. So what is di by dt protection? When a thyristor is forward bias, as you know that forward bias condition means what? Not a conduction. So here forward bias is different and conduction is different. So that's why you must aware in each instant forward bias means J1, J3 are the forward bias. Device is off state only, and it is turned on by gate pulse. So once it is forward bias, whenever you want to turn on the device, at that instant only we need to provide the gate pulses. So once if we provide the gate pulse, anode current being in the immediately neighborhood of the gate, that means you need to provide gate current between gate and cathode. So now you can see here we need to provide the voltage across gate and cathode. So that voltage will pass the gate current, minimum gate current, that is going to be 5. Thereafter current spreads. So once we are passing current to the gate, so current spreads across the whole area of the junction. Which junction? J2 junction. Our intention is to break the junction J2. Thyristor design permits the spread of a conduction to whole junction area or rapidly as soon as possible. So while you are passing the current, this spreading must be very faster rate. Otherwise what will happen? If the spreading is very slow, so because it is a congested, that current will be developed, the heat or leakage, the leakage in turn is a heat, that will be hot spot. That means temperature will be rise only very small area, that will destroy the device. So that's the reason the rate of rise of anode current, that means di by dt, is large as compared to the spread velocity of carriers. Local hotspot will be formed if it is happened, because this rate of change of current is very high when compared to the spreading velocity, because the carriers has to be spread, but that rate of rise will be lesser than the di by dt. Automatically local hotspot will be formed near to the gate, so that will be high current density. So then there is a localized heating may be destroy the device. That very simple logic here. You can see that dam inflow water is very high rate and outflow is small, then there is a congestion. So what we have to do? We have to always maintain that the spreading of the current rate is a faster rate than rate of change of the current when the gate current is given. If that is reliable operation, otherwise what will happen? This di by dt is high and the spreading is low, hotspot will be created. Therefore, the rate of rise of anode current at the time of turn on, see di by dt at the turn on must be kept below the specified limit. That is only the reason di by dt protection is required. Now we need to keep di by dt value always less than the specified value while you are giving as a gate current during on process. So now the value of di by dt can be maintained below accepted limit by using what? How we can do? By using as a inductor. that is a smoothing inductor, or you can say that di by dt inductor. We need to connect in series with the anode. So that's the reason there is a device we need to connect, because it is in the series, current is same wherever you can connect, it is in series with the device, we have to connect. That will limit the di by dt, so that the rate of change of current it can able to minimize by using as a inductor, that we can get it. So typically there is a di by dt value will be 20 to 500 ampere per microsecond. So this is the limit. It is only the microseconds of time, up to 500 amperes of current it can allowable. So that is a di by dt limit value. We can there is a specified value. You always keep that in the within the limits. Then the device will not be problem with gate current. The di by dt protection will give the because of this inductor. Local heart speed can also be avoided because of the large inductor you connected in series. That is a di by dt inductor in series with the SCR. And this can be achieved by applying as a gate current near to the maximum specified gate current. It should not be beyond the higher value. That is, these are the reasons the designer will specify in the each specification or a data sheet Ig minimum, Ig maximum. If you pass the gate current below Ig maximum, this problem will not arise. It won't be happen anything. The di by dt protection is there, but still you need to give the gate current is always below the maximum value. We have to provide such a way that gate current. So that is the range of Ig minimum to Ig maximum. To avoid local hotspot, we can an inductor is in series with that. That is already mentioned. Now next one is dV by dt protection. What is the dV by dt protection? With forward voltage across the anode, you can see that normal case, this portion I already explained in the yesterday's class itself. There is a forward voltage across anode and cathode of a thyristor. The two outer junctions are the forward bias, but the inner junction is a reverse bias. This is the normal supply is given anode to cathode. Then the reverse bias junction, what will happen? You can see there is a all other junctions outer side is already on. Here this portion J1 will be there, that will be on. This side J3 will be there, that is on. In between what will happen? J2 junction is there. So when J2 junction is there, then it is a reverse bias. That will be acting as a capacitance. So that will be, see that capacitor due to charges existing across the outer J1 junction, and then inner side, I mean this side, outer side, there is a J3 junction. So in other words, you can see that space charges exist in the depletion region around junction J2, and therefore J2 will behave like a capacitor. So once junction J2 behave as a capacitor, that is quite natural. Upper side positive, lower side is negative, and that junction is reverse bias, that will be as a capacitance act. If the entire anode to cathode forward voltage VA appear across the junction J2 only now, because that outside is breakdown, this side is breakdown, only in between junction is there. So whatever voltage applied across anode and cathode, now the total voltage will be appear across junction J2, and there is a charge is denoted by Q, then charging current is given by, we can see that charging current I is equal to dq by dt. D by dt, just Q is equal to CV notation. Here Cj is a junction capacitance, because that junction act as a capacitance. No, that's why this is a junction capacitance. Now if you just differentiate, what will happen? C into dV by dt plus V into dC by dt. So junction J2 capacitance is fixed one. The current, we can write this Cj dV by dt. So why? Because this junction capacitance is fixed one, differentiation of the constant will give 0. So only remaining portion is a Cj into dV by dt. Now, if the rate of rise of forward voltage, you can see here, this rate of rise of forward voltage is increases because device is off state. We are applying this supply across anode and cathode. Then there is a chance of getting higher voltages. Rate of rise of voltage. If it is high, then what will happen? Current also will high. This charging current plays a vital role, the gate current and turn on the SCR eventually. So what will happen? Because of this current, where we are applying this current, it is across the junction J2 only. No, we are giving, because this voltage is rises, automatically current will rise, and the current rises, then the device is going to be triggered. But whether it is our requirement is there to trigger at that instant? No. The reason is, when the device you want to fire, that is all about your control. If you want to give firing pulses, then only the device has to be fired. Or at what instant device want to fire also, you have to decide. At alpha 30 or 90 or 60 or 31, whatever the instant you want, depends on your requirement of the voltage. Only at that instant device need to trigger. But here, because of the rate of change of voltage, device is going to trigger, it is not in your control. So that is go for as a dV by dt protection. If this protection is not there, automatically wherever if you give supply anode to cathode, the device is going to be trigger if the higher voltage is applied initially, because rate of change of voltage will be high, then device will trigger. That is the reason we need to provide the dV by dt protection. So that's what I mentioned here. Such phenomena of turning on the thyristor called a dV by dt turn on method. Yesterday's class I explained now 5 turn on methods: forward voltage triggering, then temperature triggering, light triggering, then dV by dt triggering, then gate triggering. So this type of triggering I call it as a dV by dt triggering, but it is not reasonable one, it is an unwanted triggering. So must be avoided. This dV by dt triggering must be avoided. It leads to false operation. Other, if you not avoid it, what will happen? False operation. False means it is not desired point of time. For controllable operation of the thyristor, rate of rise of forward anode to cathode voltage, that is a dV by dt, must keep below the specified rated limit. So there is a value is mentioned here, 20 to 500 volts per microsecond, like what we mentioned in the case of di by dt, and here also you must keep that voltage is lesser than this, then we can avoid the dV by dt triggering. Then how to avoid or how to keep this will be lesser rate. That is the reason we can use as a snubber circuit parameter. Thyristor, the large dV by dt can be prevented by using as a snubber circuit. So what is the snubber circuit? That also I mentioned yesterday. Strictly speaking, only one capacitor is sufficient to prevent the dV by dt, because large capacitor is connected across, or one capacitor is connected across the device, that will limit the dV by dt. But there is a problem while the device is turned on. That is, once it is on, the whatever charge is there in the capacitor is sharply discharged through the thyristor. That is the additional problem. That is the reason we need to use one more resistor in series with the capacitor to operate as a to prevent dV by dt. for the higher voltages. So that is the reason we can say that using snubber circuit, you can limit the dV by dt. Using what you call it as inductor, you can limit the di by dt. So snubber circuit is defined as series connection of resistor and capacitor connected in parallel with the thyristor. We call it as a snubber circuit. So very small thing, there is a resistor and then capacitor. This setup is connected in parallel with the SCR. So that we call it as a snubber circuit. That's all. So in the each circuit we are not able to show all the protections in normal circuits and all, but inside while you are doing the hardware, whatever value of resistor and capacitors are there, this will be connected in parallel with the device. In each device, wherever if you want to use the device, this protection is very important to limit the dV by dt triggering. And we'll see how the design is going to be snubber circuit design, because as I mentioned here, using snubber circuit in a parallel with the device means this circuit, capacitor and resistor connected in parallel with the device, that only circuit, not total circuit, this alone, resistor and capacitor alone, I call it as a snubber circuit. But where we'll connect this setup, we'll connect it to the across the device. That is different. But snubber circuit is nothing but a only snubber elements, or you can say this. And in the same setup, if you want to use the di by dt also, you can connect one large inductor. So under that, you can see the connection will be now will be like this, and you can connect some load if you want. So this in parallel with the device. So that way we can able to connect the snubber circuit. Now we'll see the design aspect, because what are the design parameters here? Simply you cannot connect any value of inductor or any value of capacitor or resistor. You need to design these parameters. What is the RS, CS, L or LS, whatever. So this is a snubber capacitor, snubber resistor and di by dt inductor. You need to find these appropriate value based on what? Based on value of the di by dt max. They will give the nameplate details, no? Di by dt max, and another one is a dv by dt max. So these two values in each device they will specify. So now with the information of the di by dt and dv by dt, and you have to design R value, C value and L value to limit the dv by dt, to limit the di by dt. So that is the design of a snubber circuit. So that related to problem we'll see in the next class. If you have any doubts, you can ask me. I already uploaded that today's class PPT also in the LMS server. If you want, you can go through once. And next class we'll see what is the snubber circuit design and problem. And after that, some more protection circuits also there, temperature protection and all. So over voltage, over current, some all explanation. Then we'll move on to series parallel operation. Then you can leave.